So here we are explaining about this table. During that time, some call came, so it got cut. So now, if you are having a j omega term instead of 1 by j omega, you are having a slope of, you will get a slope of plus 20 dB. Whenever j omega or 1 plus j omega terms comes as a denominator term, in all cases there will be a slope of minus 20. That means if the term is related to a 0, then you can see it is having a slope of plus 20 dB. That means either j omega or 1 plus 0.5 j omega or 1 plus 10.001 j omega, like that. The term is coming as a numerator term, then the asymptotic log magnitude characteristics is having a plus 20 dB per decade slope. And if like this, if you can see these all are like a denominator, j omega terms as coming as a denominator term, that time everywhere you will get a minus 20 dB decade with everywhere you will get a minus 20 dB per decade, but here it is, everywhere it is minus 20 dB. Here, till corner frequency it is 0. After that, it is minus 20 dB decade. Here also, till corner frequency it is 0. After that, it is minus 20 dB per decade. So, that is explained here. Straight line of 0 dB for omega less than omega 1. Straight line of slope of minus 20 per decade for omega greater than omega 1, that is 2. Here also straight line of 0 dB till omega less than omega 2, that is 100. Straight line of minus 20 dB per decade for omega greater than omega 2, that is equal to 100. Now when you are the second, what about the phase angle characteristics? Phase angle varies from 0 to minus 90 degree and angle at corner frequency is minus 45 degree. And here also phase angle varies from 0 to minus 90 degree. Angle at corner frequency, that is omega is equal to omega 2 is equal to 100, is 45 degree. So every time you should recollect you studied the previous factors you studied, that you have to recollect it. So here, for example, yeah. If you are considering a term like this, 1 divided by 1 plus j omega t, see here, till corner frequency it is 0, after that it is minus 20 dB decay. And you can see that the angle which starts at 0 at corner frequencies it's minus 45, and at omega tending to infinity it become minus 90 degree. Now if it is in a 0 term, instead of 1 by 1 plus j omega t, instead of that just 1 plus j omega t, that time it is exactly opposite. Till omega c, till corner frequency it is 0, after that plus 20 dB per decade, and angle varies from 0 to plus 90 degree, at corner frequency it is plus 45 degree. So these basic informations or basic factors you should study and you should understand and you should by heart it, and you have to keep it in your mind. for further problems. Okay, so here also phase angle varies from 0 to minus 90 degree. Angle at corner frequency is minus 45 degree. Now we need to find we told the individual section angle, but we need to calculate the overall angle. So the overall angle of the system, that means um, this is your entire system. So you need to find the angle of this entire system. This is the entire system. So this is the entire sinusoidal form, sinusoidal transfer function, and the sinusoidal function in time constant form, that is this. So you have to find the angle of this entire term, because we find here section by sections, but you have to find the overall angle. For that, you can see here pi is nothing but for k angle is 0. We already found that, where k here is 10. K is 10. We find that for k angle is 0. Now the other term is angle of 1 divided by j omega plus angle of 1 divided by 1 plus j 0.5 omega plus angle of 1 divided by 1 plus j 0.01 omega. If 1 divided by comes, means it is a negative. So first one is 1 by j omega, angle of 1 divided by 1 by j omega, it is constant, that is minus 90 degree. Here it is minus tan inverse of imaginary term divided by the constant term. So it will become 0.5 omega imaginary term divided by 1. So here also 1 divided by 1 plus, so minus tan inverse of imaginary term, that is 0.01 omega divided by 1. Now so you have to substitute different omega value. For omega is equal to, you have to consider the corner frequency also. When it is omega is equal to 0.1, what you are getting, what angle. When omega is equal to 0.5, the angle is minus 104.3 degree. When omega is equal to 1, what you are getting, then omega is equal to 5, what you are getting, then omega is equal to 10. Yes, what is the angle? Then omega is equal to 50, what you are getting, and omega is equal to 100, that is equal to, that also you need to find, because we need to cover all the corner frequency also. So like that you have to draw it. Now we will draw the border plot. I will draw the border plot. So first term, depending on the corner frequency, we have to start. The first term at omega is equal to 1. This is a 0. At omega is equal to 1. This is 10. Yeah. Okay, we'll see that here. This is a 0 line. So this is omega is equal to 1. Omega is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then after that, this is 20, 30, 40, 50, 60, 70, 80, 90, 100. Then 200, 300, like that. It is a log, semi-log sheet. So here it is omega is equal to 1. At omega is equal to 1, the magnitude we got it. That is at omega is equal to 1, it is 20 dB. 20. And till next corner frequency omega 1 is equal to 2. Yes. Yeah. At omega is equal to 1, you got omega is equal to 1, you got a plus 20 dB. And first term, this is having a slope of minus 20 dB, so it is coming down. But the next corner frequency is omega 1 is equal to 2. So the till next line, this is omega is equal to 1 and this is omega is equal to 2. Till here, you will have a minus 20 dB per decade. For the second term, till omega is equal to 2 corner frequency, the effect of second term is 0 till omega is equal to omega is equal to 2. It is 0 dB. After omega is equal to 2, you are having a minus 20 dB per decade. So now the effect of first term and second term comes after omega is equal to 2. That means initially it was minus 20 dB. After omega is equal to 2, the second term also contribute minus 20 dB per decade. So you are getting minus 20 plus minus 20. So you are getting minus 40 dB per decade till the next corner frequency 100. So here, till next corner frequency, this is the 100. Till next corner frequency, it is having a slope of minus 40 dB. Okay, and after omega 2 is equal to 100, that is the effect of third term is coming. The third term till corner frequency, it is having 0 dB. So if you are adding this 0 with the previous effect, previous term, it is having that only, that same effect. 0 will be added with anything, you know that it will be in the previous stage only. That means till you know that if you are coming to border plot to omega is equal to 100, before it was 40 dB, till 100, the third term contribute 0 dB. That means 0, there is no effect. Then after that, the third term gives again minus 20 dB. So minus after 100, this minus 20 will be added with the minus 40. So you are getting minus 60 dB per decade. Okay, so this I will explain how the effect is coming. Okay, this will see how the effect is coming. So here, for the first term, that is 10 by j omega, or 10 by j omega term, this is having a slope of, at omega is equal to 1, it is having plus 20 dB, and after that it is having a minus 20 dB decade. So here it is having a magnitude of like this, and after 20 it is having minus. This is the first term effect. Now the second term effect, that is 1 divided by 1 plus j 0.5 omega. It is having effect of till omega is equal to 2. This omega is equal to 1. Now if you are taking a graph for the second term, till omega is equal to 2, it is 0. After that, it is having minus 20 dB per decade. So this is minus 20 dB per decade. This also minus 20 dB per decade. Now for the third term, that is 1 divided by 1 plus j 0.01 omega. It is having till 100. It is till 100 omega is equal to 100. It is 0. After that, this will be minus 20 dB per decade. Now when you are adding these all terms, okay, when you are adding from omega, so now we put a straight line. Here omega is equal to 1. Here omega is equal to 2. Here omega is equal to 100. So now when you are adding, this is omega is equal to 2. This is omega is equal to 2. Till omega at omega is equal to 1, it starts from omega is equal to 1, it starts from plus 20 dB. Plus 20 dB. At omega is equal to, starts from plus 20 dB. Then till omega is equal to 2, second term gives 0. So till omega is equal to 2 and third term also gives 0. So only first term contributes. So it is having minus 20 dB. Till omega is equal to 2. It is having minus 20 dB. Then here omega is equal to 2. From omega is equal to 2 to omega is equal to 100. Third term is 0. Second term gives a minus 20 dB and first term also gives minus 20 dB. So from omega 2 to 100, it gives a minus 40 dB. So the slope is changed from here, minus 40 dB. Then after 100, this 20 minus 20 dB, this minus 20 dB, this minus 20 dB. So after 100, you will get a 40 minus 40 dB and minus 60 dB. So this is minus 60, this is minus 40, and here it is minus 20. So this is the that is why you are getting a slope like this. Now correspondingly you should plot the using these values for different values of omega. So you have to plot the corresponding graph. Okay, you need to plot the corresponding graph. Now the second part of the question is you need to find the gain crossover frequency, phase crossover frequency, gain margin and phase margin. So now what is gain crossover frequency? Your for your this dark line is your main diagram. Now the gain crossover frequency, okay, gain crossover frequency, what is gain crossover frequency? So we'll see the definition. The gain crossover frequency omega g is defined as the frequency at which the resultant magnitude is 0 dB. The gain crossover frequency is defined as the frequency at which g j omega h j omega is equal to 1. So resultant magnitude crosses 0 dB, that is gain crossover frequency. Then what is phase crossover frequency? Phase crossover frequency omega p is defined as the frequency at which the resultant phase is minus 180 degree. The phase of frequency is defined as the frequency at which angle g j omega h j omega is equal to minus 180 degree. Now what is then gain margin at the phase cross of frequency, what is the difference? And the phase margin is at the gain cross of frequency, what is the difference between these graph? So when you are coming to this graph, you can see that gain crossover frequency is, here it is 1, 2, 3, 4. So you are getting it as gain crossover frequencies 4.7. At the 4.7, this graph crosses 0 dB. So that is 4.7. Now, what is phase crossover frequency? That means, yeah, you have to see that where the phase crosses 180 degree. So I think that when you are observing it, it is not at this is 10 frequency line, this is 20. So here just after that it is clearly crossing. So phase crossover frequency is 21. Okay, for this our problem. Now, what is phase margin? Phase margin. So every time you should see that diagram. What is phase margin? The phase margin is at gain crossover frequency. What is the difference between minus 180 degree and the phase diagram? And gain margin is at phase crossover frequency. What is the difference between 0 dB and the corresponding gain? So this you have to observe it. Now you got here as gain crossover frequency as 4.7. You have to see that at that frequency, what is the difference from 180 degree to your phase curve? So the difference is almost 16 degree, and if it comes above 180 minus 180 degree, it is plus 16. If it is come below, it is minus. So here it is phase margin is 16 degree. Now you need to find the gain margin. So here at a phase crossover frequency, you have to draw a straight line, and you have to see the difference between your actual plot with the 0 dB line. So the difference is at this point, we can observe that it is approximately equal to 26 dB. It is 26 dB. So the gain margin for this graph is 26 dB, and when it comes below the 0 dB, it is plus. If it comes above, it is minus 26 dB. If it is come above, it is unstable system. Here also, if phase margin is coming below this, then it is again an unstable system. Now, the second part, the other part of the questions, also determining the value of K and the corresponding phase margin for the gain crossover frequency of 10 radians per second, 15 radians per second, and 1 radians per second. Now, now this is the actual graph. If gain crossover frequency is 10, then this entire line should pass through 10 frequency 10 at omega is equal to 0. That is why this graph should be shifted for if GCF is 10. So what is your question? You can see that what is the question. You need to find, also determine the value of K and the corresponding phase margin for the gain crossover frequency of 10 radians per second, 50 radians per second, and 1 radian second. So if it is 10 radians per second, then if it is 10 radians per second, so the graph should be shifted in such a way that this graph should cross at 10 radians per second. Now, in order to find the value of k, now you can see that, this will be, graph is, should pass in such a way that at omega is equal to, the graph should pass through 0 dB line at omega is equal to 10. Omega is equal to 10. Now, now at omega is equal to 10, when you are observing it, the gain is minus 14.2 dB. Okay. So here you can see that from the Bode plot we observe that omega is equal to 10 radians per second. The resultant magnitude is minus 40. At omega is equal to 10, the resultant magnitude is minus 14.2 dB. For it to become the gain crossover frequency, the resultant magnitude plot must be raised by plus 14.2 dB. That is we did here. This graph is shifted or raised or shifted by plus 14.2 dB. Now the open loop gain is to be multiplied by K1 such that 20 log K1, that is equal to 14.2 dB. Okay, so gain, it should be multiplied by the gain. So that is equal to K1 such that 20 log K1 is equal to 14.2 dB. So K1 is equal to log inverse of 14.2 divided by 20. So it is equal to 5.1. Since the given open loop gain is 10, the value of K must be equal to 10 into 5.1, so 51. So you know that given gain is, here it is 10. Now you got an additional factor of 5.1 if it is raised to that level. So then the equal to 10 into 5.1, 51. For the given crossover frequency omega g is equal to 10 radians per second, the value of, for this value of K, the phase margin is 51 degree. No, phase margin is at that time the phase margin. So at when this graph is moving through graph is crossing the omega is equal to 0, that time the phase margin is 5.1 degree. That is they explained. But k equal to, since the given upper loop gain is 10, then for the overall gain, the value of k must be equal to 10 into 4.1. That is 10 into k1. That is 51. Now next question, if you are next you need to find also determine the value of k and the corresponding phase margin for the given crossover frequency of 50 radians per second. So now from the border plot we observe that omega is equal to 50 radians per second. The resultant magnitude is minus 44 degree. Now when you are coming, this is 10, 20, 30, 40, 50. At 50, the resultant magnitude is, around minus 44 dB. Okay. For it become the gain crossover frequency, for it to become the gain crossover frequency, the resultant magnitude plot must be raised by 44 dB. So that in order to, this should be raised like this. It should be raised plus 44 dB, so that you can see that yes, at 44 dB at up to 50 radians per second it crosses 20, 30, 40, 50. 50 it crosses this line. Okay. So raised by 40 plus 44 dB. So the upper loop gain is the upper loop gain is to be multiplied by k1 such that 20 log k1 is equal to 44 dB. So k1 is equal to log inverse 44 divided by 20 is 158.5. Since the upper loop gain is done, then what you need to do is you need to multiply 10 with the 158.5. You will get a 150,585. Now the gain crossover frequency for omega g is equal to 50 radians per second. That means for the gain crossover frequency omega g is 50 radians per second. For this value k, the phase margin is you can see that the phase margin is at when this line crosses 0, this is 0 dB. When this line is crosses 0 dB, that is 50. Let us see that the phase margin is minus 24 degree. So for k is equal to this much value, for gain crossover frequency of omega g is 50 radians per second. For this value of k, the phase margin is minus 24 degree. The same way for omega is equal to 1 radians also, you can see that for that you have to shift the line down like this. So here you can see that there is a 20 dB plus 20 dB shift. You can see that So here the question is also determine the value of k and the corresponding phase margin for the gain crossover frequency. Gain crossover frequency of omega is equal to 1. So now gain crossover frequency, if you want 1, this is omega is equal to 1, then this line should cross at omega is equal to 1. In order to cross, you have to shift this one down. So you will get this graph. Now you can see for the border plot, we observe that omega is equal to 1 radians per second. The resultant magnitude is plus 20 dB. For it become to gain crossover frequency, the resultant magnitude plot must be lowered by minus 20 dB per minus 20 dB. So at omega is 1 radians, actual result magnitude is plus 20 dB. In order to become this as a gain crossover frequency, we have to shift the line 20 dB down. So that is lowered by minus 20 dB. The optimal gain is to be multiplied by K1 such that 20 log K1 is equal to minus 20 dB. So K1 is log inverse of minus 20 by 20, that is equal to 0.1. Since the given loop gain is 10, the value of K must be equal to 10 into 0.1, that is equal to 1. For the gain crossover frequency, omega is 1 radians per second. For this value of K, the phase margin is at omega is equal to 1. You can see the phase margin is 61 degree. So all of you go